Okay, this video we're talking about the first law of thermodynamics, second law, and also entropy. Starting with the first law of thermodynamics, it's talking about the conservation of energy. It's basically a restatement of that. Previously, we talked about how you can have work, and the work would be going up a hill, for instance, and go into gravitational potential energy. And it would be stored as that. And then if you let it go down the hill, the gravitational potential energy could turn into kinetic energy as the cart rolls down the hill. And that's conservation of energy. And so the first law of thermodynamics with respect to heat energy. And so if you have an input of Q, heat, which is kind of like the fire, and it will change the internal energy of the system, U. And so if that is a engine, for instance, it will raise the energy of the molecules on the inside of the engine, and that will allow us to get work out, and so that we can do work. When we're talking about these things, the signs have to do with whether or not the energy is going in or going out. So for instance, when Q is going in, you're raising the energy, and so it's a positive Q. When Q is going out, like for instance, if you were to ice it, you would lower the energy. And so we talk about work in or work out. And so work in is when you're putting work into a system, like you're squeezing it, like in the case of a bike pump. Or work out is, for instance, in a car where the pistons are pushing out. So work in or work out. And that's a restatement of the law of conservation of energy with respect to heat. And so we're able to follow the transformation of heat energy through the system from heat to internal energy to work and vice versa. And that is the first law of thermodynamics, conservation of energy. The second law has to do with heat flow or energy flow, and it always goes from high to low. And we especially talk about that with respect to heat engines. And so here I have a simple piston engine, and there's the little shaft there, and there's a piston in the middle, and it's connected to a rotating, like a crank, which will give us work. And I'll have a spark plug along with energy here that is provided by gasoline, for instance, or diesel or wood. And the energy will go in here in the form of heat energy. And then I'll have an exhaust of some sort. And that energy will be the low side, or the heat that is lost. And then I'll be able to do work here with this reciprocating system that's turning this crank. And so heat energy can be described by the equation. The work that you can do in a heat engine is related to the difference between the high heat side and the low heat side. And that will describe how much work we can get out of a heat engine, and it relates back to the equations that we have here. But specifically with heat flow, if we don't have a difference between the high heat side and the low heat side, we can't do that. This works with steam engines. It works with our Stirling engines. It works with steam turbines. It works with internal combustion engines like this one, or external combustion engines like the trains and that kind of thing. And that's the second law, which is energy moving from high to low, and we incorporate that into the idea of heat engines, the ability to be able to get motion out of the heat flow. The last thing is entropy. And entropy is a measurement of disorder. And in the universe, disorder always increases. And so the barn is a good example of this. Left to itself, the barn over time is going to get messier and messier. Entropy is going to increase. So over time, the entropy or the messiness of a system is always going to increase. Now, this is also evidenced by your room, right? So maybe your room has gotten messier and messier over time, and I guess there's nothing you can do about it. It's just going to get messier and messier. But check it out. Here I have two backpacks, and the first backpack looks really messy. And so that is the law of entropy, that over time, it is going to get messier and messier. But there is something you can do about it. And you can decrease the entropy of a system by doing work on it. And so now this doesn't break the laws of thermodynamics, because when you do work on something, when you put work into it, you're going to clean the backpack, and you're going to fix up the barn, you're going to clean your room. But the truth of the matter is, you've made energy, or you've released energy in the form of heat. Now you're sweating, right? You've done such hard work that you've got sweat pouring down your brow, and you're saying, "Gee, Mom, I had to clean my backpack," and that was work. And you've increased the energy of the universe by all that heat that you're putting off as you're doing your work. And so that doesn't break the law. You're actually making more entropy in the universe. You're just making less entropy in your backpack. So a real good example of entropy is in your car. Entropy typically ends up as heat, and so the energy ends up as heat. So this is where you have transformation of energy. We have gasoline, which is very concentrated energy, and we put that in our car. And where does the energy go? Well, the energy of our gasoline goes into kinetic energy to move us down the highway, and in the end, you come to a stop. And so, what the heck? Where did all that energy go? So the energy itself is not stopped. The energy actually went off as heat. All the energy really in the end ends up as heat. And the more the heat we have, the more spread out it is across the universe, the more entropy we have. And so that is the three laws of, or actually two laws of thermodynamics. And the first law being conservation of energy with our equation there that allows us to follow the transformation of energy. The second law being heat flow, and heat engines especially showing us a good example of how heat flows and how we can do work out of that. And the third thing is entropy, or messiness, is that things typically go from order to disorder. We can change that by putting work on it or doing work on the system. But in the end, entropy always wins out, and we always make more messiness than we had in the beginning. And that's the two laws of thermodynamics.